such a collaborative. I didn't even realize I actually calculated that. Where it's really neat.
It is. It puts things together. I like, especially when you get to Gen 7. Basically, all the algebra that you've been learning for the last however many years you've been in school is what Gen 10 is basically. It's how to actually use it. All right. Let me double check the speaker real quick. There it goes. Cool. So who's ready for finals week? Do it. Let's crush it and then take a week off. We'll be back. Anybody have? So for this review session, I'm just going to go through the problems that you all want to go through. Talk about how I'm likely to grade things. If you have questions about what you're thinking for like the definitions page or whatever, or we can just start working through from front to back. Any questions that you have? How do I want you to explain elements? Well, so you're not sure what to say when it comes to what an element is. You can always say what defines one element versus another. What's the difference between two elements? Somebody said protons. Number of protons in the nucleus. So you could say it's matter made up with a specific number of protons in the nucleus. Would be one possible answer. So in order to make it so it's a little bit more well-defined as far as what I'm looking for, I'm going to reframe these as short questions. And so that it won't just be give me a definition for atomic mass. It would be something like, what are the units on atomic mass? Or how does atomic mass help us find moles? Something like that, so that you can have a little bit more of an idea of what I'm looking for. Because these are kind of open-ended, right? And I do, so if you can answer it with a simple equation, like if I said density, you could just write D equals M over B. That's a full credit answer. If I say, give me a definition and you give me the equation, that's fine. Any other questions on this page?
Mole. Just put an exact quantity of atoms.
Yeah. So like, or you could even say 6 times 10 to the 23rd objects.
Okay.
Would work. Right. So that what I'm really looking for this first page is for you to show me that you know what the terms are. Not necessarily a dictionary definition. Right. So I'm fairly loose with these. On the other hand, I very rarely have a 10 out of 10. Most people get about a 8 to 9 out of 10 on this front page, which is fine. You don't need a 10 out of 10, especially considering this is the one that has the most uncertainty is what I'm going to put on, right? Most of the other things, you know exactly what the question's going to be. This one's a little bit undefined still, because I could pick a lot of different things. But just use it as a way to show me that you know what that term is, even if you don't have a perfect definition for it. Definition questions are hard. I still remember when I was in grad school, so I was in a 5,000 level chemistry course with a bunch of chemistry PhD students, and the instructor asked us to define what an orbital was. And out of a bunch of chemistry PhD students, nobody had a good answer for it. Right, so it's hard to answer definition questions about, especially when it's about a weird topic or something quantum. It's really hard to define. So Don't worry about getting it perfect, show me what you know. Any other questions on this page? Where does everybody want to go next? Should we just go to number 2? Okay. Can I do number 4? Absolutely. Maybe. There we go. Okay. So for number 4, this is going to be the trickiest one, right? It's not going to look exactly like this. This is a percent error question because we have subtraction on top and then we're dividing and then multiplying by exactly 100. The fact that we're changing, it's going to be something where you have to change operations though. It's going to be a mixture of addition, subtraction, and multiplication, division. So this is the trickiest one on here by far. So the trick with switching our operations when it comes to sig figs is every time we switch operations, we have to do our rounding, right? Because how do we decide whether our multiplication rules are more important than our addition subtraction rules? We just do the rounding every time we switch back and forth. So the first operation we have to do here is the subtraction piece. So 2.255 minus 2.266 is negative 0.011 grams. Right, so subtraction, so we're keeping the same uncertainty. So we're going to 3 decimal points. And now we have division. And then there's an absolute value on there, which just tells us we're just going to get rid of the negative sign there. Right, so just like we did in percent error when we did that specific heat lab, we don't care which direction we're off, and so we put in an absolute value. We just want to know how far it is away from the real value. So basically it just tells us we're going to ignore that negative sign. But this means we only have 2 sig figs. Right, because we did the subtraction first, now we only have 2 sig figs. And so when we do the division, we get a number. Zero zero 48788. 004, yeah. We're still gonna have to multiply by 100%. That's underlined, so it's an exact number. Good sneeze. Good sneeze. Once we're only down to only 2 sig figs though, remember these zeros, none of those zeros count as sig figs. Zeros to the left of the first non-zero number don't count as sig figs. Right? So we get to keep 0. After we multiply by 100, it's going to be 0.49%. Our units canceled out, right? We had grams on top and grams on bottom, so they go away. All of our percentages are going to be unitless technically, right? Because in order for it to be a percent, you have to have the same units on top and bottom, or else it doesn't work. So percentage should always be unitless. And that's why you usually need more information about what you're talking about. If I just say something is 10%, that gives you absolutely no information what I'm talking about, right? In this problem, this is your full credit answer. The trick is you'd be tempted if you just counted sig figs at the beginning, you didn't stop and do it one step at a time, you'd be tempted to keep 4 sig figs because everything has 4 sig figs up here. But after we do the subtraction, we only get 2 sig figs. How do we feel about that? Basically, the two easiest problems that I can put for number 4 are a temperature conversion or a percent error, because those are our two common equation or common calculations that involve both sets of rules. So it's going to be one of those two. If it looks a little bit different, it's still going to be, here's a subtraction addition piece and here's a multiplication division piece. Do it in the right order, do your rounding before you switch. Cool? All right, anything else on this page that looked confusing that you want to talk about? No?
I just wanted to double check that 3, because the 0.25 minutes is so negligible, it just becomes 146.
Correct. So our calculator answer would be 146.25, but we only get to keep the same uncertainty as our least certain number, which is another way of saying the same number of decimal points as our number that has the fewest decimal points. So we're going to the hundredths place here or to the ones place here. So we're going to keep our uncertainty in the ones place, round to the ones place. Yeah. All right, any questions about units? Reminder, it's on the top and the bottom, it's going to cancel out, right? So our units here would be moles. We're adding or subtracting, our units don't change. 1 mile plus 3 miles is 4 miles. Our units are identical. It's only when you multiply or divide that our units change. How about nomenclature? How about it? It's great, isn't it? It's awful. I'll acknowledge that. So for 4, bromine is one of our diatomic elements, right? We had a list of basically column 17, and then oxygen, nitrogen, and hydrogen. Those are all the elements that are naturally found when they're in their pure form on Earth. We find them as these diatomic molecules. So number 4 would just be bromine. It's not bromide because it doesn't have a negative charge. It's not dibromine. Those are both really common answers. I see that all the time. It's reasonable. We just have to remember that for that column 17, oxygen, nitrogen, and hydrogen, their pure form as an element is like this. So Br2, Cl2, I2, F2, O2, N2, H2. All of those, if I said O2, that's just oxygen. Right? And so we actually specify when they're not in this state because this is the most common state. So if you actually did have just an oxygen atom, we would say it's atomic oxygen, meaning it's oxygen that's not present as O2. There are a few of these that also have different forms, like for instance, ozone is pure oxygen as O3 instead of O2. It gets its own name because of that. But these are the most common diatomic elements, right? And so out of the 10 questions here, one of them is going to be a diatomic element. Either I'll write one of these and you just have to write the element name, or if I just say oxygen, you're supposed to write O2. Okay? But as long as, yeah, Brooke?
So, fluorine is included in this, then why is number 2 calcium fluoride and not calcium chloride?
So fluoride is when you've got fluorine with a negative charge. A good question. So if we have fluoride with a negative charge and we have calcium with a 2+ charge, we need 2 of them to balance it out. it's not that we're saying that there's a fluorine molecule attached to a calcium atom. It's that we're saying it takes two of these fluoride ions to balance out the charge. That's a good catch. Thank you. Right, so when it's, even if it's F2 or O2 or anything else, if it's part of an ionic compound, it gets that I suffix because that means that it's negatively charged. So it's only when it's by itself and neutral do we say just bromine or just fluorine. So chloric acid, ic came from an 8, right? So we need chlorate. So chlorate looks like this. So then the acid form is add enough H pluses to make it neutral. It's only a -1 charge, so we only need one H plus. So HClO3. Okay. I think I'm actually going to change the format a little bit to make it look a little bit more like our nomenclature worksheet that we did for lab in week 6, where it says what type of compound is it and then what is the name, because that lets me give you more partial credit. So half a point for each of these is going to be, is it an ionic, acid, or covalent or element? And then half a point is actually giving me the name of the formula.
Study that.
Yeah, so if you go back to lab 6, that nomenclature lab, and that whole last 2 pages was basically what type of compound it is, and then what's the name. I'm going to make it look just like that. And because the idea is not to make you do more work, it's that I can give you more partial credit. If you at least acknowledge that it's an acid, then I can give you half a point, even if you got the name, right? So know how to recognize it, and that should help you organize your thoughts when it comes to naming too, right? Because as soon as you know it's an acid, you know you're not worried about ionic and you're not worried about covalent. You just have to follow our acid nomenclature. Any others on here we want to talk about? Going once? We can always come back to it.
So, so like number 5 versus number 6.
Mm-hmm.
How do we remember when to do when it's just or then when to do the parentheses?
So if it has parentheses, first off, what type of compound is this? It's ionic, right? And selenium tetrafluoride is not. Selenium tetrafluoride is covalent. So if we know that, okay, then if it's ionic, I'm just saying the name of the 2 ions, right? So manganese 3 means it's got that charge, and sulfate looks like that. So our actual formula would then be, we need 3 sulfates for every 2 manganese. Right, because we need these charges to add up to 0. And the lowest common multiple of 3 and 2 is 6. So we need +6 charge from the manganese and -6 charge from the sulfate. So that takes 3 of these and 2 of those.
What's a good mix?
Well, we all memorized them for our polyatomic ions quiz, right? So hopefully you still remember them, but I'd go back and review them. The one tip that helps, almost all of our polyatomic ions were -1, -2, or -3, right? Most of them were -1 or -2. Your total number of electrons in all of our polyatomic ions, they're all even. And because that's how you get something stable, is to have all of your electrons paired up. You can't have full valences if you don't have an even number of electrons, right? So if you're trying to remember that sulfate is a -2 charge. If you're deciding, I can't remember if it's -1 or -2. Well, sulfur has 6 valence electrons, right? And each oxygen also has 6. So without counting the total number of electrons, we're not going to actually draw the Lewis-Stokes structure for that. We don't need to. But as soon as we see that all of the atoms involved have an even number of electrons, that means my charge has to be even. Because we need everything to have an even number of electrons for it to be stable. So if I'm trying to remember my charges, that's a good way to double check it. Oh, it was sulfate -1 or -2? It's got to be -2 because that's the only way I get an even number of electrons. And so same with nitrates, same with the chlorates, and etc. Right? Because chlorine has an odd number of electrons, right? If chlorine has an odd number of electrons, the charge on a polyatomic ion has to be odd as well in order to make it so that everything has an even number of electrons. Right? So that's a good, I can't remember that. That's how you can figure it out from raw principles we already know. Is just all of your total number of electrons will always have to be even. It's not a perfect system. It still means that you still have to remember, okay, what's phosphate? I know phosphate is going to be an odd number, but I don't know if it's -1 or -3. There's still a little bit of memorization in there, but it helps. Going back to this, so if we know that selenium tetrafluoride is covalent, we're not worried about what charges are. We also don't know how to specify how many of everything is if we don't have charges. So that's where those prefixes come in. So as soon as we know it's covalent, we know that all we have to do is say how many we have of everything. If it's ionic, we let the charges determine how much we have of everything. And that's why we have a difference in how we name them. Did that answer your question? Yeah.
Since we knew what is forward. That's coming.
You could call it covalent, and I would give you full credit, but you could also just say that it's an element.
Okay.
The better answer would be it's elemental bromine, or just that it's an element. But it is also a covalent compound. So. Everybody remembers which of our periodic or which of our elements always have the same charge. And we don't need a Roman numeral on this one because it doesn't have my periodic table there. When we're looking at the periodic table, there we go. There were 6 transition metals. This isn't actually P table, this is Google. No wonder it's garbage. It works for our plane right here though. So this whole column is always +1 when it's an ion, right? This whole column is always +2 when it's an ion. Everything else that's a metal almost everything else that's a metal has variable charges. And that's why we need the Roman numerals, right? Who remembers which are the 6 transition metals that don't need Roman numerals, that always have the same charge? Silver, zinc, cadmium, aluminum, gallium, indium. Those 6 always have the same charges, so they don't need Roman numerals. If they don't need Roman numerals, we just need to know what their charges are. Aluminum, gallium, and indium make sense. They all have, well, aluminum doesn't even have a d orbital. Gallium and indium both have a full d orbital. So if they've got a full d orbital, they're never going to break it up. So these three are always +3. Aluminum's got 3 valence electrons. So when it's stable, it's a +3. Same with gallium, same with indium. Zinc and cadmium, same logic, different number. Zinc and cadmium have 2 valence electrons in a full d orbital. So they're always going to be +2. Silver is our weird exception. It actually does have a full d orbital. If you look at the electron configuration for silver, it actually, instead of, so for silver, it looks like, so silver is going to look like krypton, and then it's going to be 5s1 4d10. Because basically what happens is the silver borrows an electron, the d orbital borrows an electron from the s orbital so that it can be filled. And so that's why it's a little bit of an exception. I'm not going to ask you to come up with this off the top of your head. I'm not going to ask you about the exceptions here. But that explains why it's always a +1, because it only has 1 valence electron to lose. Right, so for these 6 metals and these first 2 columns, we don't need Roman numerals. Every other metal is going to have a Roman numeral to say what the charge is. There are a few others in here that really only have 1 stable charge, but I'm not going to have you memorize these ones because they follow our patterns and they're all together and they're more common than the other ones. Are why I want you to focus on having these ones down pat, having them memorized. I want to say iridium, maybe. Iridium is always a +3, but even I don't have the other exceptions memorized.
Just to be sure the bottom right are all negative.
And then all of the non-metals over here, they're all non-metals because they're trying to gain electrons to be stable. So they're always going to be negative. Boron's a bit of an exception. So remember that these ones listed as yellow are sometimes called metalloids because sometimes they behave as a metal, sometimes as a non-metal. They're right on that boundary. So boron actually is more commonly found as a +3. So it behaves kind of like a metal, but it doesn't have metallic properties. It's not conductive and things like that. So, but I don't teach you to pay too much attention to the metalloid aspect because textbooks can't agree on what counts as a metalloid and what doesn't. Some textbooks will put aluminum as a metalloid. Some textbooks will even put carbon as a metalloid. So because there's a lack of uniformity there, I'm not going to have you use that term all that much. Yeah, that's not helpful. All right, any other nomenclature questions? So once again, it's going to be really hard to get this perfect. I don't expect you to get it perfect. Get me most of the way there, and you're going to get 9, 8.5, 9 points out of this, right? You might be able to get it perfect, but it's also totally reasonable to not. This one though. This one, I would love to give every person in this class a 10 out of 10 on this page. It's doable. Especially for protons, neutrons, and electrons. I don't want to mark anybody down here. You all know how to do this. You don't, this is one of the easiest skills to pick up at this point. Right? What tells us number of protons? The element, the atomic number, right? Number of protons is the same as the atomic number. So for sulfur, that's 16. And for gallium, 31. So we can fill those in right off the bat. This is also the page that's probably, not only is it the page where you can get a lot of points, it's also should be a really fast page too. So this is, if you're planning out, hey, I have 2 hours to do 10 pages. You have this one down pat, not only is that close to 10 guaranteed points, it'll also only take you about 2 minutes. And then you're done with it. Right? So this is, make your points on this one. Plan around it. So sulfur is going to be 16, gallium is going to be 31. How do we figure out neutrons? Yeah, this is the mass number. So neutrons is just, neutrons plus protons is equal to 33 for sulfur, for this sulfur atom. So 16 plus 17 gives us 33, right? So protons plus neutrons equals mass. Just occurs to me, I've never actually checked whether or not Zoom captures the when I use this version of the marker, which is one of the reasons I always use PowerPoint. So it doesn't.
Yeah, that's fine.
Okay.
It's weird.
All right. Well, I'll keep that in mind. Thank you, Corbin. So then gallium, mass number 71. Of those 71, 31 of them are protons. So 40 are neutrons. And then what's going to tell us the number of electrons? The charge and the atomic number. Right? So sulfur doesn't have a charge on it. If it doesn't have a charge, electrons is the same number as protons. If it does have a charge, start from the same number. So start from 31. And if you know it's started with 31 and has a +3 charge, it must have lost 3 electrons. So that tells us it has to be 28. Here's what we can do. It'll actually capture the board work for the rest of this. And what we will open up a blank PowerPoint. There we go. 16, 17, 16, 31, 40, 28. So then for the electron configuration, we're just counting on the periodic table, right? So for sulfur, we're always going to start at 1 s, and it holds 2 electrons. Then we're done with the first row of the periodic table. Second row of the periodic table, We're over at lithium and beryllium. So we're back in the S block. And it can hold 2 electrons still. Then we jump over to the P block, which can hold 6 electrons. That gets us to neon. Back to the S block, third row, S block, 2 electrons. 3p, not 6, 3p4. That gets us to sulfur. If it has a charge, we still start by writing the electron configuration by like normal, and then we adjust it. So for instance, if I said it was sulfide, so it was the 2- charge. 2- means it's got 2 extra electrons, right? So starting from here, can we put 2 extra electrons into a p orbital? Yeah, that fills the p orbital, right? So we would just take it, we'd erase the 4, and we'd change it to a 6. So then gallium. When are we allowed to use our noble gas shorthands? When it's past argon, when it's got more than 18 electrons. So for gallium, the last, if we wanted to use that, the shortcut, we could. I'm going to write it out by hand. 1s2, 2s2, 2p6, 3s2, 3p6. That gets us to argon. 4s2, 3d10, 4p1. Now it's gallium when it's neutral, when it's in its metallic state. It's not neutral. It's got a +3 charge, which means it gained or lost electrons. Lost electrons. And it lost 3 of them. Which 3 electrons do we remove? We're going to take that one away. When you take 2 more away, we're not going to break up the 3d10. We're going to take the valence electrons first. The valence electrons are the ones in the 4th energy level here. So our final electron configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, no 4s2, 3d10, no 4p1. Right, so this is your final answer here. Or in our shorthand version, we could write it as argon in brackets 3d10. Both of those are full credit. Both of the blue ones are full credit. Right, but I'm going to say this again. Don't use the shorthand unless you're more than 18 electrons. If you're more than 18 electrons, you can use this. But this is the same as argon's electron configuration, right? For the one we wrote out for the sulfide here. You can't just answer that as, I mean, technically you can. I'm not going to give you full credit for it. If you said this to another chemist, they'd say, yeah, sure, that's a great way of writing it as shorthand. But for this class, I'm specifically testing you on, do you remember how to do this piece? Right, so you're not full-fledged chemists yet. You're just baby chemists. Which means we leave the training wheels on. All right, any more questions on this page? All right, let's look at. Our conversions here.
Feel bad here, going website, so they.
No, it's okay. I don't like the other one anyway because I can't erase it. I gotta clear the whole thing. So. All right. Key point here. Using only equalities provided means only the conversions that are on your conversion sheet. I don't care if you have some conversion that converts feet to meters directly. If you have that memorized, that's great for you. That's not a way to answer the question in this class. In this class, I want you to stick to using only the conversions that are on your sheet so that you can show me you know how to do that. It also helps cut down on people trying to use their phones cheap because your phone's not going to give you the steps anyway, and it's going to give you a shortcut, which means I don't give credit for that. On the take-home test, that'd be a different story because you're allowed to use outside resources. I'd still prefer if you use the conversion sheet conversions, but I'm not going to mark you down if you use something you found on the internet, unless it's wrong. All right, so the way these conversions are going to go, there's going to be a straightforward length one. I'm going to make you go through multiple steps. I'm not going to give you one you can do in just 2 steps. So centimeters to miles, kilometers to feet, something like that. Right? That's going to make me show, or I'm trying to make you show me, you know how to do multi-step conversions. 2 is going to be temperature conversion. If I give you Kelvin to Fahrenheit on the practice test, there's a decent chance that Fahrenheit to Kelvin would be how I'd ask it on the test. Right? If I'm looking at this as a student and I know that this one's going to be a temperature conversion, I would know how to do it Kelvin to Fahrenheit. But then if I was thinking as a student, what's the easiest way an instructor could trip me up? Would be to just do the reverse conversion, right? So I'll either just, most likely, I'm not going to commit to anything since, because I want you to still be on your toes a little bit. Don't just memorize things. Most likely, I'll either change the number and leave it Kelvin to Fahrenheit, or I'll just switch Fahrenheit and Kelvin. What's 78 Fahrenheit and Kelvin? You still have to go through the steps to get there, right? And watch your sig figs because temperatures are tricky when it comes to sig figs because of those addition conversions. Yeah, let's do it.
Are 32 and 1.8 exact numbers?
32 and 1.8 are exact. So that's for the Fahrenheit, 1.8 Celsius plus 32. 1.8 and 32 are exact. The 273.15 number is not. That's a measured number. So 78 Kelvin. Remember, temperature in Kelvin equals temperature in Celsius plus 273.15. So solve for temperature in Celsius, we need to subtract 273.15 from both sides, which is going to give us negative 195.15. Do we get to keep 0.15? Because to get TC by itself, to solve for it, we have to subtract 273 from this side. No worries. It's hard to learn all this stuff while you're also reviewing algebra. It's what makes this class really tricky. All right, so we're plus or minus 1 in Kelvin, which means our answer in Celsius needs to be plus or minus 1. So it's just going to be negative 195. Degrees Celsius. Now we plug that into our Fahrenheit conversion. Temperature in Fahrenheit is 1.8 times negative 195 plus 32. Now we're multiplying. So we're going to keep it to 3 sig figs. And we get negative 451, 351. So after when we keep our 3 sig figs, it's still plus or minus 1, right? Our uncertainty is still in the ones place, which means when we add the 32, we're still going to keep it to the ones place. So our temperature in Fahrenheit is right. So it looks like we did gain a sig fig, but we kept the uncertainty in the right spot, and we followed all of our rules. You follow all your rules, sometimes you gain or lose a sig fig. That's just the nature of conversion. Right, and so there's going to be 4 problems on this page, right? Which makes each of them 2.5 points. This point of this problem of this page is not to test sig figs. I still care that you're paying attention to them, but if you mess up the sig figs on this one, it's -1/4 of a point. It's not that big of a deal. On number 2, when I'm specifically testing you on do you know your sig fig rules, and the math's already set up for you, that's where I'm going to be a little bit more strict, where messing up the sig figs would be more like a 1-point deduction, because that's the whole point of page 2 is do you know your sig fig rules? The point of this page is can you do the conversions? Full credit means you have to keep track of your sig figs, but you can still get a 9 out of 10 and still mess up your sig figs on every one of them. It's the caveat to that. It's -1/4 point unless you're way off. If you wrote down your final answer was negative 319.1723 Fahrenheit, that's wouldn't be the actual calculator answer anyway, but that's way off on the sig figs, right? The further your sig figs are off, the more points I have to take off. If you're only off by 1 sig fig, it's a 1/4 point though. The third one is going to be either area or volume. It's going to be something with the higher powers units that you have to do. Remember how to do that. I'm going to cube the whole conversion factor like we did to the gas laws one. Remember with the area of the plunger? So you're going to have to do something where you square or cube to get full credit on 3. And then 4 is going to be a combined unit problem. Well, yeah. Let's look at this one. Actually, I'm going to do it right above 3 so we have a little more space. 1.000 yards cubed. First off, if you can put a real world idea for how big that is? Does anybody know what a cubic yard looks like? Yeah, like a pallet. A pallet is about a cubic yard when it's loaded. That's a really good analogy. I go back to when I had to spread mulch when I was working as a gardener. We would buy 2 cubic yards, would fill up the bed, a full-size bed of a pickup truck with mulch. So, but a pallet is an even better way to visualize it. So that's what we're talking about. So our number should be roughly how many liters would you say, or how many 1-liter bottles of soda could you fit in a pallet? Probably like 20 by 20 by 20 by, sorry, 20 by 20 by 4. We have like standard soda bottle sizes. So we're looking at something like 800 liters, roughly, very roughly, just making it up in our head. But that's going to tell us if we get the right answer, right? That's how we're going to do our reference check. So before we do anything else, we think it's going to be maybe about 800 or so liters. You don't have to do that or show your work for that. But this will just keep you from, so that you know if you screwed something up. So 1 cubic yard, how can we get to liters? Well, we can go from cubic yards to cubic feet. We know we can go from feet to inches, which means we can get to centimeters cubed. And we know that a centimeter cubed is a milliliter, right? So then once we get to centimeters cubed, we can go to liters, because that's on your conversion sheet too. So there's our roadmap. 1 yard is 3 feet cubed. 1 foot is 12 inches cubed. 1 inch, 2.54 centimeters cubed. And 1,000 cubic centimeters is 1 liter. So this is where you want to practice with your calculator to make sure you know how to plug it in properly. But 1 times 3 cubed times 12 cubed times 2.54 cubed over 1,000. How about that? We're actually not so far off. I get 764, 765. We're keeping 4 sick days. 764.6. Right, so if we didn't do this, if we didn't do a reasonableness check, we can still look at that. Okay, there's 750 liters that sound about like a pallet, and not too far off. If you entered it incorrectly, or maybe if you cubed the 1,000, you're going to get a number that's less than 1. If you get a number that's less than 1, your intuition, your physical understanding of how space works should tell you that that's a mistake, right? Because you know what a liter looks like and you know what a cubic yard looks like. If you get less than 1 liter is equal to a cubic yard, you did something wrong. Now, under a time situation, you might not be able to figure that out, but I can give you a 1/4 of a point extra if you get the wrong answer and you can't figure out why it's the wrong answer, but you know it's wrong. You can write, I'm pretty sure this is wrong, but I don't know where I messed up, and I'm moving on. It's not going to be full credit answer, but I can at least give you a little bit of help. Okay? You got 900? Okay. How do we feel about this one? Easy as long as I'm the one up here with the pen, right? All right, and the last one. The last problem on the conversion page is a combined unit. So either a speed, like this one, or a density. If I gave you grams per milliliter, could you put it in pounds per gallon? Something like that. If I give you miles per meters per second, can you put it in miles per hour? How do we do those? There's two approaches. What's your approach, Carmen?
Oh, I have.
Okay. Yeah, if we know that it's 343.2 meters per second, we can say that we can go 343.2 meters and convert that to miles. And then we can go 1 second into hours. And then we can just do the division at the end, like we did figuring out our, we were figuring out densities or molarities in that last lab, in the titration lab. We wanted a molarity, so we found moles and we found liters, and we just did the division, right? Same just here, find miles, find hours, and do the division. So 343.2 meters. 1 meter, 100 centimeters. You can, for this one, there's two options also. Because on your conversion sheet, we've got a kilometers to miles conversion. So you can either take meters and go to kilometers, and then kilometers to miles. Or you can go meters to centimeters to inches to feet to miles is the exact way to do it, but it's more steps. How do you figure out which one's better? I have the conversions, the exact conversions memorized better. So I'm going to go that way, even though it's more writing. But if you wanted to say 343.2 meters, 1,000 meters is 1 kilometer. Is it 1.609? So I do have that one memorized too, but I don't like it because it's still approximate. Anybody who's done any running on a track? How many meters is a lap? That's a mile. That's 4 laps. So one lap is 400. So we're talking about 343 meters is a little bit less than a lap, which means for our reasonableness check, we should be getting something a little under a quarter of a mile. We're doing it the long way. Well, inches, 1 foot, 5,280 feet is 1 mile. Both of us should give us the same answer within sig base. Times 100 over 2.54 over 12 over 5,080. 0.2133. When you do the short route, you should get same thing. Most of the time, that's how it should work out. Sometimes the rounding doesn't happen exactly the same, so it'll be off by 1 in that last digit. Both of these are equally valid. Both full credit. where I would caution you is if we're starting from a number that has more than 4 sig figs, you have to remember this number is not exact. That's an approximate conversion, which means if we started with 5 sig figs, we'd still have to round to 4 sig figs if we went this route. Versus if you started with 5 sig figs and used all exact conversions, you'd get to keep all of your sig figs at the end. Well, you'd still get to keep 5 sig figs. Right? That's the only time where these are not equivalent in terms of full credit. Is if you go an approximate route, you have to remember to round it proper. So, for instance, on number 1, started with 5 sig figs. If you take the route that uses this conversion, your answer should be rounded to 4 sig figs for number 1. If you take the exact route, you get to keep all 5 sig figs. I'm not going to say that either one is better. They're both full credit, but you've got to get your sig figs right for full credit. Okay. All right. Can we take 1 second and go to hours? Yeah. We actually have a 1-step conversion for that. 1 second. For every 3,600 seconds, that's 1 hour. So we get a really small number. How do we know how many sig figs to keep here? The 1 is exact, really. When we have it in the denominator of a unit, we're assuming that their measured number was up here. So we're assuming we have at least that many sig figs on the 1. So we want to keep at least 4 sig figs here. So when we do our division, we still get to keep 4 sig figs. And then we're just going to take 0.2133, divide by this number, and I get 767.88. Which we're going to then round 4 sig figs. Because we had 4 sig figs where we started. Anybody know what that number is? It's a real speed. Yep, speed of sound at sea level. So, which means this is also Mach 1. Is 767.9 miles per hour. Again, at sea level, planes don't usually fly at sea level. So it wouldn't actually be quite the same. The speed of sound does change slightly depending on the pressure. All right, how do we feel about that one before I erase everything? If you wanted to do all of it as 1 step, then awesome. At this point, I wouldn't be trying to learn that if you don't already know how. If you don't know how to do your combined conversions all in 1 row, don't worry about it. Just do it as 2 steps. This is a simpler, more intuitive way to do it. And we're not in the business of trying to learn new things 48 hours before the test, right? We're in the business of trying to get as many points as you can with the skills you have. Unless you're feeling really confident about your grade and you really want to learn some new tricks, I'm not going to tell you no. But make sure you're spending your time wisely. All right. We've been in here an hour. Should we take a break? Should we just keep going? Do a break? 35%. I switched the weights on the quizzes and the final exam because of the answers I was getting on the quizzes. Right? At this point, I still don't have a better answer for AI work other than only grade the stuff that you do in front of me. So that means labs and the test is going to be the bulk of your grade. All right, let's take a break. I'll start working through the next one or answering questions in 10 minutes.
Do you round grades? Like if it's like an 89 or like I just bump it up to an
It depends. It depends on how close you are. Depends on the students. It
Okay,
depends
so
on
like
how
what if
many
I
of
got
them.
an 89 point like 5 or something, I mean I never really turned in, what would that be?
Everything's turned in, or at least most of your stuff's turned in. You've been showing up all your labs and everything. It's typically around class. So
Okay, so
I would usually around.
Okay.
If there's only one person in class sitting at 89.5 and they not show up and they are not returning any work, I'm not gonna round that score up.
Yeah.
Just because that wouldn't be fair with them and say that, because we can't do pluses and minuses here. I wish we could, that would be easier. But I'm not gonna say somebody who hasn't been showing up to lab, should get the same grade as somebody who's got a 99. You know what I mean?
Yeah, no, that's fair. Okay, thank you.
No problem. At 1:30, I have somebody else coming to do the day already anyway. You can start at 1:30 if you want, but I'll be here.
The what?
I'll probably be, I think I'll still take it, there's two of you, but you come to the lab. Yeah, let's come to the lab, and I'll see if I can find some more comfortable chairs than the stools that are in there. Yeah,
So I was stuck on the end of this lab here.
yeah,
So I just, for the life of me, I can't remember what equation am I supposed to do here. This is the one I can remember, but I don't know what to put for temperature. So
I see your graphs.
tell me if I'm doing this wrong too.
So you're close.
Okay.
The equation of the line means we want equation of this trend line.
So would it be the R2 or is it?
No, so double click on the trend line, and have you draw it so that you will remember it better.
Thank you.
And scroll down. Keep going. So under trend line, see where it says label? Right there.
Oh, yeah.
It says custom hit use equation instead. Now close out of there. Gotcha. So if you know the equation for that line is it's y equals that, right? So it's y equals, no, it's okay. 4.29 10 to the minus 5 times x, and then there's an intercept there too, right? Minus 0.0134. What did you plot on the y-axis for that one?
Sorry, what do you mean by that?
What's on the y-axis here?
It's the one divided by B.
So instead of y, we can write 1 over volume. And what's on the x-axis?
Is pressure.
Pressure in torr or pascals.
Oh, it's in torch, if you switch over to Pascal.
Either way, as long as you were consistent when you added everything up, that's fine. You just need to know about it.
Yeah,
Because
I had it in Pascal and I converted that to torch.
Perfect, that's fine. So what this question is asking is, if you have this equation,
Okay.
it's saying, if you plug in our atmospheric pressure for P,
Okay.
what is the volume?
Thank you so
No problem.
Oh, and then, I just total brain fart now. I realized that I've been using my phone as a calculator. Would that be needed in during the exam? As long, because you said at the beginning, you can kind of tell. But should I try to get more from the library?
I would recommend doing it that way, because then there's just no question about it. So if you're comfortable using a TI-83 or something you can get from the library, I don't want you to switch horses midstream, you know what I mean? And now don't know how to use it. Like, make sure you know how to do your pH and make sure you know how to do scientific notation.
Okay.
And if you're good with that, I would use one of their calculators.
So,
No problem.
You have pushed.
Yeah, just a quick one. On the take home, I didn't know, I mean, the whole kind of conversion to go back in the volume of the spheres 2 centimeters. Should I look this one up online? Is that all right to do?
It's all right to do. The other thing you can do is, if you have this, if you know volume, you just have to solve it off. So it's just doing some.
Yeah, that was the part
Okay,
that I
yeah.
actually didn't know how to do, how to solve for R in that case, so.
So divide by 4/3, divide by pi, and you'll get
R Q.
you'll get volume over. So that's the same as equals RQ, but you could actually just have that.
Oh, that's how it.
That's where it comes from.
Oh, okay, yeah, yeah. that makes
So
sense.
then, to get rid of this, take the cube root. If you don't know how to plug that into your calculator, you can just raise everything to the 1/3. Is the other way of cube root, or square root for that matter, is raising something to the 1/2 power.
That makes sense.
So you can get there from this equation, but this isn't now for a class. So if you had to look up how to do that, then you're fine.
All right, thank you.
So what happened here, that's the same number, but off by a couple factors, 10, right? So what you're missing is parentheses around the bottom part. Thank you. Sorry. So the denominator, the old magic. Insert means that you're gonna, instead of writing it, that you're gonna stick something new in there. So it does. Well, so, but that's okay. Like, you got 8.2, it's set out 8.8, just means that you round it spot.
It's probably like that happens on the exam. Like, torsional.
It all comes down, so if it's just the rounding and the last digit is off, we're not gonna take any points off at all, as long as you've rounded to the right number of segments. What I will say is, I think you've missed decimal point.
Yeah, it still does 8.2.
It's still gonna be 8.2, but that's okay. 767.8 is the same as 767.9 when it comes to the segments, right? So, yeah, you were missing that one. And it's probably because you forgot to divide by 1,000 when you get your meters to kilometers conversion.
I told him figure it out.
I got all the same answers. It took me a while just to figure out how you got there. It's because I don't feel it. But
So part of it is gonna be, so multiplied by 100. I think you missed this, you missed a You missed the decimal point somewhere. Because that's the right number, but it should be 0.21, not 2, because think about it. 300 meters is not 2,000 miles.
I got like this thing like I don't know because it was like the like it was the fact that it's all well yes I was you know how sound was they're able to like share what the things mean.
Oh, yeah, I forgot it. I forgot it.
So on the test, if you showed all your work properly and then somehow didn't reduce the calculator error, it will give you most of the points for it. So on a 2.5 point problem, a calculator will be like 1.5 point. Okay, so not that big a deal.
Now I see confidence.
Good.
I just had to say. Yeah, yeah, she's. Like I want something to go. I want to talk about because of the yeah. I'd say it's all secret. That's because she asked. She didn't want. Oh, how many girls do we know? I'm like artsy as it is. We just say that. So it's not like we're so bad. Yeah, that's what we're saying. Like I was.
All right. Who's ready to tackle the calculations part? The tricky part. Well, we'll start with the Lewis dot structures first. All right, so what are our steps for Lewis dot structures? Count valence electrons. Pick center atom. Attach other atoms. Fill valences until you run out of electrons. So for carbon tetrachloride, counting our electrons. We're at 7 chlorides. Each chlorine has 7 valence electrons, plus you've got 1 carbon that's got 4 electrons. So that's going to give us 32. What's gonna go in the middle, carbon or chlorine? And why? It has 4 vacancies. The other way that we have it determined is you look at the electronegativity, right? If you have things that have the same number of vacancies, whatever's less electronegative goes in the middle. So carbon meets both of those criteria. And then we're just going to surround it with the chlorines. And we know right after that, they have to all be attached. How many electrons did I use attaching them? 2 for each chloride, or sorry, for each chlorine. So that's a total of 8. So we're down to 24 electrons left. Now, like you can technically go in any order you want. I usually find it easier to start at the outside and work in, especially when it's an isommetrical molecule like this. I've got 4 chlorines, and each chlorine still needs the same number of electrons. How many chlorine or how many electrons do I still need to add to fill a valence? I need to get to a total of 8. And each of these chlorines already has 2 electrons from the bond. So that means each chlorine still needs another 6 electrons. What's 6 times 4? 24. So if I fill the rest of the carbon or the chlorine valences, we've used all of our electrons. Now the question is everything happy? The chlorines, we just started by filling all the chlorine valences. Are the chlorines good? Yeah. The chlorines all have a total of 8 valence electrons. Chlorines are all happy. What about the carbon? Carbon also has 8 valence electrons already, right? If the carbon's got 8 valence electrons, it's also happy. I mean, more bytes in here, but it's stable would be a better way to say it instead of saying it's happy. So use the right number of electrons. Everything has a full valence. We're good. Boom. How do we figure out the molecular geometry? Yeah, we need to count the electron domains, count how many things are taking up space around the carbon, which gives us tetrahedral shape. And if we have 4 things taking up space around the carbon, we're going to have that tetrahedral geometry. If you don't want to memorize the word tetrahedral, that's fine. You could write tetrahedral, but you could also draw it. As long as you get the bond angles relatively close to right, and you use those wedges and dashes to show the 3D shape where it's appropriate. A tetrahedral geometry will always look like 2 things that are roughly 120 degrees, or actually 109 degrees, but 120 is a third of the way around the circle, so it's pretty easy to estimate. These ones that are 120 degrees from each other are flat in the plane of the board. And then we've got one thing sticking out and one thing sticking away from us that are the other third of the way. They're also about 120 degrees from the other 2. So they're kind of on top of each other. You can kind of estimate. It doesn't really work with your hands very well. We're looking, but it should look like a symmetrical 3-sided pyramid. is the overall shape here. So that's the electron geometry, because it has 4 electron domains. So the electron geometry is tetrahedral. I asked you about the molecular geometry. What's the difference between molecular geometry and electron geometry?
Except for N.
It still stays in the same shape. It just means you can't see the electron pairs. So the electron, if you had a lone pair, it would still take up space, but we wouldn't be able to see it. So, yes. So we'll see that in a second. So for instance, if we looked at ammonia, Lewis dot structure looks like this. That's still 4 electron domains because the lone pair still takes up space. So the electron geometry is still tetrahedral. The molecular geometry it's not trigonal planar because it's still basically if we look at what the shape is, we say that lone pair is in the plane of the board, and then we have a hydrogen here, and then a hydrogen down and into the board, and a hydrogen coming out towards us. It's trigonal pyramidal or trigonal pyramid. But the good news is you don't need to remember it. I would at least memorize these ones because the basic electron geometries, it's only 3 choices for you right now. It's either linear, trigonal planar, or tetrahedral. All of the versions that are just missing one thing because it's because it has a different number of electron domains, or a difference between the electron domains and number of lone pairs. Those are less valuable to memorize the name of. Trigonal planar. Trigonal planar means flat. Planar always means flat. The trigonal would be, there's 3 pieces. Those, if you don't memorize all of the electron geometries, you just have to be able to draw it with approximately the correct bond angles. So as long as you can do that, you don't need to memorize their names. But you got to pick one of those 2 routes. So in this case, because the carbon has 4 electron domains, the electron geometry is tetrahedral, and because each of those domains has an atom attached to it, we can see all of them, which means our molecular geometry is also tetrahedral.
So just write tetrahedral. That's what we want us to write.
If you just give me the name, that's full credit. If you can't remember the name, I'm just trying to give you 2 options to get to full credit. You can either do it spatially, showing it me, the shape, or you can give me the name of the shape. I never liked being told you just have to memorize this because I said so either. So this is my way around that. All right, and then if we're trying to talk about polarity, is this polar or not? What are our 2 criteria for polarity? Has polar bonds is one of them. Polar bonds and asymmetric shape. Let's change colors. So if I was answering this on the test, I would just make my little checkbox. Does it have polar bonds? Does it have asymmetry? Is carbon to chlorine a polar bond? How do we know? They share electrons, they're not the same electronegativity. Right, and it's greater than that. We said that our threshold for considering something polar was a difference in electronegativity of at least 0.4. Right, so carbon to chlorine, if you check your electronegativities on that, on your conversion sheet or on your periodic table, is a difference of 0.5 or is it 1? It's 0.5, huh? Sorry, I forgot to give you more 6/8 on that chart. So it's a little bit more than 0.5, which means we do have polar bonds. Do we have asymmetry? No. So yes, the chlorine is more negative than the carbon, so the chlorines are all pulling the electrons towards themselves, but there's 4 chlorines all pulling in exactly opposite directions. So everything is going to cancel out. So this is like 4-way tug of war between NFL teams. It's not really going to move very much. Right, so if we don't have asymmetry, we could say non-polar. For it to be polar, you have to say yes to both of these. Greater than the difference between carbon and hydrogen. Use carbon and hydrogen as your benchmark. So as long as it's a bigger difference in electronegativity than carbon to hydrogen, it's polar.
Does a single double bond count as asymmetry?
No. So, are we good with this one? All right, so let me split it for it. If we did, if we looked at nitrate, for instance, nitrate's going to look like the Lewis dot structure for nitrate is going to look like this. So its molecular geometry is going to be trigonal planar because it's 3 electron groups, electron domains. How do I know where to put the double bond? I just picked oxygen at random, right? So this actually gets to a property of electrons that shows up a lot, especially when you get into organic chemistry. If there's 3 equally valid places where I can make the double bonds, it's not really like it picks one and the other 2 stay as single bonds. It's sort of like it's taking turns. So it's more like there's 1 1/3 bonds to each oxygen. So actually each of these oxygens is symmetrical, even though we draw it this way. It doesn't, but you're kind of say that.
Yeah.
Well, it turns out resonance is a really tricky thing. And my organic chem students that are both 2 years ahead of you in terms of how many chemistry classes they have are still struggling with it. So for now, it means we have to have a different atom attached here. If I replaced one of these oxygens with a chlorine, now it's asymmetric.
Right.
We just need something attached to that central atom that's not the same as the other. So it can be a lone pair, it can be a different atom, it can be both. But you need something to be different to have that asymmetry.
Somewhere we looked at on a periodic table.
So that periodic table doesn't have, if you look at the practice test, there's on the periodic table sheet, there's a bunch of electronegativity values pulled out separately, right? Okay, so that's what you would use. All right, should we do SO2 now?
Yes.
Okay. It's been a long time since we've done these ones, right? We've been focusing so much on stoichiometry. Why we have a review session. So SO2. So sulfur's got 6 electrons and there's 1 sulfur plus 2 oxygens. Each oxygen has 6 electrons, valence electrons. We have 18 electrons to work with. How do we decide what goes in the middle? Oxygen's more electronegative, which means it likes to share less. Oxygen's going to try and share as little as possible, which means sulfur goes in the middle. And we know the oxygens have to be attached to the sulfur, so we can use 4 of our electrons right there. How many does each oxygen still need? 6. So that's going to use up 12 of our remaining electrons. So we can't put any more electrons on the oxygen, but sulfur still needs some electrons. We only have 2 electrons left, so let's put them right there. Are we good? Not yet. Our oxygens have full valence. We use the right number of electrons. However, we don't have all of our valences filled. So if we don't have all of our valences filled and we're out of electrons, we have to take a lone pair and turn it into a double bond. Right, so that's when double bonds come into play. When you run out of electrons before you're done filling all the valences, then you have to get them to share more than normal. So that's a full credit Lewis dot structure. And that if you checked answers on the internet, that's not what the answer on the internet looks like. That's okay, because I didn't teach you anything beyond this. This is the full credit answer I'm looking for, even if it's not the best possible Lewis dot structure, because you don't know enough yet to get the right one from scratch. So for now, this is our full credit Lewis dot structure. Gen Chem, we're going to learn why this isn't exactly right and how to fix it. But I've also had people ask me, how do I know? How is it really obvious when you're using outside resources that aren't from our class when you're using AI? One of the ways is if you solve a problem that I give you using methods that I didn't teach you, and you're more correct than what I've taught you in this class, that's kind of a red flag usually. So if you stick to solving things the way that we do it in this class, it makes it really obvious for me to see whether you're looking things up or doing it on your own. Fine? Yeah. So we're sitting right here, right? We used our last remaining pair of electrons to put on the sulfur right there, and now we have no electrons left. We have no electrons left, but sulfur doesn't have 8 electrons yet. So the sulfur needs 2 more electrons, but we're out of electrons. So the only way we can do that is by making one of these lone pairs into another bond. So when you do it that way, you just have to be careful, make sure you don't forget to erase as well. If you're actually taking a lone pair and turning it into another bond, not just throwing more electrons in. All right, what's our electron geometry look like then? What's our basic shape? How many things do we have taking up space around the sulfur? So we have three things taking up space. I'm actually not going to draw the lone pairs on the oxygen because they're not going to affect the shape of the sulfur. So we have three electron domains. Lone pairs still count as electron domains because they still take up space. Double bonds only count as one electron domain because they have to be in between the same two atoms. If it's a double bond, even though there's 4 electrons there, they're still stuck between the sulfur and the oxygen. So it only takes up one space. So if we have three things taking up space, our electron geometry. So if you drew it like this, full credit, as long as you get it close to 120 degrees on these. If you're going the route of using the name, we'd say that the electron geometry, you don't need to show the electron geometry because I only asked for molecular geometry. But if we're showing all of our work, say the electron geometry is trigonal planar, and the molecular geometry we just can't see this. It's still there taking up space, but we can't see it. So it's bent. Again, so if all you did in this box was write the word bent, full credit answer. The more you show your work, though, or at least explain your logic, the more partial credit I can give you if you're wrong, though. Right? So if you're very confident on this part can go really fast too. If you're not sure about your answer, explain it a little bit, and that way you can get another point or so, depending on how good your logic is. I'm not going to give you a ton of partial credit if you explain your logic and your logic is totally wrong, but if you're halfway there, I can give you halfway there points. So we have three things. If the normal shape is this three-sided, this triangle shape, but we can't see this top piece because it's just a lone pair, it looks like it's trigonal planar but missing a piece, so they call that bent. No problem. All right, let's do polarity. We're still the same two criteria, right? Sulfur to oxygen's polar. Oxygen's on our Mount Rushmore, right? Oxygen's one of our most electronegative elements. So without even looking at the numbers, I know that oxygen bonded to anything besides another oxygen is a polar bond. And then, does it have the asymmetry? Yes. Because the electron geometry does not have three identical things around it, it's not symmetric. Therefore, polar. And again, this is one where I don't really want you to just be guessing all over the place. Try to be internally consistent. Because if you get your Lewis dot structure wrong, let's say you forgot your lone pair, maybe you miscounted the electrons, and so you wound up with this structure instead. If you got this structure shouldn't be bent. If you got this as your Lewis dot structure, then your molecular geometry would just be linear. If you got your Lewis dot structure wrong, but then your molecular geometry was correct compared to what you drew, I can give you full credit for your molecular geometry. Right? If this is your Lewis dot structure, but then you draw this for your molecular geometry, I have to mark you down twice. Because not only did you get your Lewis dot structure wrong, you also drew your molecular geometry wrong compared to what you had to work with. Right? So it's more important to be consistent with your own answers than it is to get it right. It seems counterintuitive, but I mark right answers down all the time because it doesn't match with what the student gave you beforehand. Right, so be consistent, and this is where you'll see. In this case, I would say that this is right but inconsistent. So if I was grading this, I'd write RBI, right but inconsistent, and I'm going to mark you down. If you said, okay, well, this is my Lewis dot structure, so my molecular geometry is linear. Then I'm going to say it's wrong but consistent, and I'm going to give you full credit for it. Okay? It just so happens that both of those acronyms happen to be baseball terms. I didn't plan that. I didn't even realize it until I started writing them on people's papers. But WBC is our World Baseball Classic that we just finished. And RBI is run batted in. Is everybody excited for opening day after your final? The Giants get the first game of the season against the Yankees in New York on Wednesday night. I'm excited. All right, questions on this page? Then there's 3 stoichiometry problems in a row. The good news is number 7 should be a full credit answer, full credit for everybody, and should be quick. Because I'm already giving it to you in moles. So, hear me when I say this. If everything is already in moles, and I'm only asking for an answer in moles, don't try to use the molecular weight here. You'd be amazed at how many times on a time pressure, people will start trying to convert moles back to grams before they do their stoichiometry, and they get totally lost. If everything's already in moles, we can answer this question as soon as we balance it. We can answer this really quickly. So if we know we have 2.44 moles calcium chloride and 1 mole calcium chloride makes 2 moles silver chloride. We can make that much product, right? And on the other hand, if we have 4.10 moles of silver nitrate and it's 1:1, which one's right? Yeah, the lower number. That tells you what the limiting reactant is, but it also tells you the theoretical yield. We only have enough ingredients to make 4.1 moles of silver chloride, even though we have enough calcium chloride to make 4.88. Right, so that right there, that's full credit, 10 out of 10 for this problem. Don't overthink this one. 7's going to be simple. Sorry, we're missing one thing. Precipitation. If you're not sure, if you just wrote not redox, then you can get 1 out of the 2 points for this. So this part, balancing and figuring out the theoretical yield, is 8 out of the points. 8 out of the 10 points here. Telling me the reaction type is 2 points. So you just said, I don't remember what it's called, but I know it's not redox. I can give you half credit on that.
And all redox take water.
That's all acid-base reactions. And it's not all of them, but most of them are going to make it water.
As far as precipitation goes, the way that I read that was aqueous solid on one side. Is that really the test?
Yeah, for precipitation reactions at this level, that's all we're looking for.
Okay.
If you mix 2 ionic solutions together and it makes a solid, that was precipitation. It also means that nothing changed charges. So that's how we know it's not a redox reaction as well. Nothing changed charges or oxidation states. But yeah, if you can, there's only 4 types of reactions that I've taught you so far, right? So if you can memorize what the clues are for each of them, you don't need to think about oxidation states.
Is it possible to have, well, maybe not in this, but what's the precipitation reaction or actually in my
Kind of. Basic in the more general sense, precipitation means that you made a solid out of something that was in solution.
Okay.
There are a lot of ways you can do that. This is just the most common way. I shouldn't have, huh? Mathematically, it's not going to change anything, but it should be 2/2. I just wrote it wrong because I was looking at how many nitrates were attached to the silver instead. So I said 1:1, but because 2/2 is the same as 1.
You put one.
All right. So 8 and 9, I might flip the order on so you can't just automatically know, like just memorize the order of what types of reactions they are. But one of them is going to be a gas loss question where you have to use PV equals nRT to get to moles, or use moles to get to a pressure or something like that. And the other one is going to be a pH problem. So one's gonna, if we know one's pH problem, one's a gas loss problem, you know what you're looking at there. The only way that the gas loss problem can change is if instead of making it atmospheres of product, if I gave you atmospheres of a reactant and you had to get to moles from that. Basically, if I switched sides of this equation, asked you how many grams of solid you're gonna make, if you started with this many moles or this much pressure of a gas. But so I can move things around a little bit, but the gas loss question is going to be PV equals nRT. You're either going to know the moles and have to get the pressure, or you're going to know the pressure and have to get the moles. Right, and this is where our molecular weight comes in, right? If I give you grams of a reactant or product, then we're looking at molecular weights. Right, and our last way of getting to moles is if we have a solution in a concentration. Okay, so we just got practice with that last week in lab. And we did a bunch of practice problems last week in class too. And then the wild card question. Number 10 is going to be some sort of a word problem. Something similar to stuff you've done, but it's going to be a little bit different. I'm going to ask you to think on your feet a lot. It's not going to be a super complicated word problem. but it's gonna ask you something about, give it to you in a word form and then ask you to solve something about it. If I were looking at this as a student, trying to get ready for the test, what's the biggest topic that we talked about in this class, did a whole lab on it and everything, that doesn't show up anywhere in this test? Yeah, we haven't touched anything. 1 through 9 did not mention energy at all. But we did spend like a week and a half talking about energy, right? So if I was gonna guess, it's gonna be something related to energy. Again, I'm not committing to that. I'm just telling you, if I was a student looking at this practice test and looking at what's missing, right? Because what you don't want to do as a student is get into the habit of, oh, here's the practice test, I don't need to study anything else. Right? You want to look at the practice test and say, what's missing from the practice test that they could change up? Right? I'm not trying to trip everybody up, but on number 10, I'm going to give you something that's a little bit different. And odds are, it might be energy related, might be quantum related. We didn't touch anything with wavelength or frequency in this test, and we did spend a significant amount of time on that, right? Remember that lab where we looked at the light, the different types of light and wavelength and things like that. E equals H times C. Sorry, E equals H times frequency. So you might see some frequency units or wavelength that might have something involved there. But basically, the only 2 places on this test where I'm going to ask you something that might be a little unexpected is problem 1 with the definitions and concepts, and problem 10 that's a word problem. 2 through 9, you know exactly what's going to be on there. That's the whole point of the practice test. Okay, so for problem 1, I would just go back and look at read your notes, look for vocab, look at your labs, what did you spend time on lab that doesn't show up here, that I might be able to ask you about, so densities, uncertainties, things like that. And then at least be able to get a halfway decent plan for number 10. Me telling you it's a wild card question is hard because it means how do you prepare for something that you don't know what it is, other than study everything. But you can kind of guess based on what's missing from the test.
Okay.
Yeah. All right. First off, let's balance. We've got calcium hydroxide making water. We're making calcium iodide with 2 iodines in it. If it's 2 iodines, there has to be a 2 there. You need to get 2 iodines somewhere. One calcium and 1 over here. But that means we have 2 hydroxides and 2 H pluses. They're 2 waters. All right, so we're balanced here. 1.636 grams. Thank you. 74.092. 1 calcium plus 2 oxygens plus 2 hydrogens. Then to get the moles over here, we're going to use 450 milliliters. 1,000 milliliters is 1 liter, and 1 liter is 0.104 moles. If you're comfortable with the algebra or the math here and you want to combine these into one conversion factor, that's totally fine. If you're not comfortable with that map, just leave it like this. So we get then for our calcium hydroxide, and I did mess up over here. We good so far? So now we need to know what's going to run out first. Because remember these pH problems, if we have our hydroxide and our acid on the same side, one of them has to run out first. So this is an excess reactant problem. Also, just before I forget, I meant to say this earlier. Sometimes when I go write these tests, I'm just working from this problem basically. I'm just going to go into this problem and change the reaction and change the numbers. Sometimes I forget to change the numbers up here. Don't trust the ones in the description. Trust these ones. These are the ones that I'm double checking more often. I oftentimes forget to change those numbers. Okay, so when in doubt, and if it looks like it doesn't match, because sometimes what'll happen is I'll fix the numbers up here, but I'll forget to change HI to HNO3 or something like that. If you see a mismatch, go with what's written this way, okay, for this class. And then if you're taking the test with me in person, you can always ask me, like, hey, looks like you messed up over here, or why don't I see the same things? You might not want to tell me that I messed up. I take it well, but if you're not feeling comfortable saying that, you can just say, how come I don't see the same things in the problem description as right here? And I'll say, oh, I messed up. So you can only, but if you're not taking the test with me, if you're taking it with SAS and they can't get a hold of me, or you can always just make a note, I think this is what you meant, and cross off the top part, and I'll grade it that way, because that is what I meant. All right, so excess reaction problem. We want to know what's going to run out first. Can we look at it and guess what's going to run out first? It looks like this is going to run out first because we're using it up at a 2-to-1 ratio. If I double this, I'm going to get 0.044 something, right? That's less than 0.068. So I'm pretty sure I'm going to have leftover acid. So if you think you know what the limiting reactant is, start from there. Say, okay, 0.02208 moles calcium hydroxide. And for every 1 mole calcium hydroxide, that's 2 moles HI used. And we'll get 0.04416 moles HI used. Do we have that much? We have more than that, right? So we guessed right. If you guessed wrong on what's going to run out, you're going to get an answer that doesn't make sense. Because if I did this math and it came out to be, I don't know, 0.048 moles HI used, that can't be true, right? because we don't have that much HI. So if you ever do this step and you get a number that doesn't make sense, you just probably means you picked the wrong limiting reagent. It's probably the other thing is the limiting reactant. This is why we stress the reasonableness check, right? Because it tells us when we thought we had it right, but then we messed up. As long as we're still going back and checking, hey, it can't be that. So we started with 0.0468 moles HI. And we're going to use 0.04416. Then it's 0.0026. Left over. We only get to keep 4 decimal places, so we're gonna have to round it to the 10,000th place. Are we done? I mean, class is done, but I figure we want to finish this real quick. We're almost there. Question says, what's the pH? So we know how much acid is left. So we have 2 choices. We need to switch colors. We can either say pH is equal to negative log of H3O plus concentration, or we can say 14 equals pH plus POH. When do we use the bottom one? Say it louder. Right now? No. We use the bottom one when we have leftover hydroxide. If hydroxide is what you have in excess, then we're going to find POH and then do 14 minus POH. That'd be the reverse of this. In this case, we have leftover acid. We have leftover acid. We just need to know the concentration of the acid, and we take the negative log of that. All right, so for this one, we're not using that equation. All right, last step. In order to get the pH, we need concentration H3O plus, which because this is a strong acid and we're only doing these questions with strong acids, we can say our concentration of the acid is equal to our H3O plus concentration. Which means we just need moles of HI divided by final volume. Moles of HI left, right there. And our final volume is the same as our initial volume. We didn't mix 2 solutions together, we just dumped a handful of solid into our solution. We just need it in liters, so it's 0.450. So that means our concentration is 0.0058 moles per liter. So last step, and I know that's like the third time I've said that. But this is all part of the last step. Last step is negative log of 0.0058. Which should be something between 2 and 3. 2.3 maybe. 2.24. And we always write these out to the hundredths place, 2 decimal points on every pH. Now we're done. So that's the longest one that you have by far, right? If there's one problem that I would say sums up most of what we've learned in this class, it's this one. Because you gotta balance, you gotta get to moles, you've gotta do limiting reactant, excess reactant, and then you have to find your concentration and then take the negative log of it. So we talked about strong acids versus weak acids. Weak acid just means it doesn't split up 100% in water. But I'm only asking you about strong acid. When you put a strong acid in water, 100% of the time that strong acid gives the H plus to a water molecule.
And then that is an acid, okay?
Yes.
Um,
1 calcium plus 2 oxygen plus 2 hydrogen. It's just added up. That.
Oh, not going to grams. Oh my god.
There it is. Yeah. Final state times left. I'm a baseball fan, but I'm a Giants fan.
I was born and raised in San Jose, and so it's Giants to me. And then in Little League, I got put on the Dodgers. And the parent. So I've been a reactionary Dodgers fan ever since.
That's fair. My son is a very big Giants fan, and he had to be on the Dodgers in the league year, and he was not about it. It was hard to cheer. I said go blue.
Go blue.
I should say go blue. I can't say the other one.
That's really interesting. I get it's my brother's birthday coming up, so I get to go to the not opening, the first home game.
Oh,
On Friday. This next upcoming week. I'm so excited.
I'm gonna be there. I'm gonna be there the next day. They're playing the Astros, right? Yeah, we're gonna go to the Saturday game.
Oh, how bang. I wish I could come across you, but have fun. And it's my first time going to a professional game since '06. So I'm pretty excited.
It's really fun at the Rivercat Stadium because it's so small. And my son was having a conversation with, we went to see the Mariners there last year, and he was having a conversation with their left fielder.
No way.
And there were $30 tickets. So, yeah, it's fun. You'll have a good time. Yeah. Oh, thank you. So yeah, it's Sacramento starts for pro sport.
Yeah.
Like we had some indoor soccer for a bit, and we had teams, but we don't like to have games. Yeah.
Question,
Yes,
will we get a tracing sheet or you want?
a fresh one.
Okay.
So it won't have any notes or anything on it. But I'm gonna give you the same way that it is on PDF of the practice test. That's what I'm gonna give you. So it'll be the full equation sheet, electronegativity values with pressure periodic table.
So you're giving
We
us
can't
the last
we can't
papers?
use
I'm giving you the last 2 papers. You can't use your own.
No, that's why you're giving us a new one.
I'm gonna give you a fresh one. But if the very first thing you do when I hand it to you is you flip it over and you box those 6 elements to remind yourself about them.
Like just even the
Or-
balance, like charges, and then all of those are. Is it okay? Like, okay, if we walk, so like.
Yeah,
Okay.
you just have to start, so you only have to have it memorized for 5 minutes until I give you the paper and then you rewrite it on there, or. You have to have to know how to use the periodic table.
And then
Which-
equation sheets for like Kate's, like, the conversion. Yeah.
Yeah.
Okay, yeah.
So the same,
Sorry, I did scroll, but I just closed.
so it's the same equation sheet we've been using, the whole thing. And then convert the periodic table looks like this, and this is where your electronegativities will be.
Awesome, thank you.
No problem. Right, so you don't have to have those means.
You know
Yeah.
how there's two equations? If we get that equation wrong, like if we use the wrong one for the question on the test, like it's gonna mess the entire.
It will, but
The
it'll-
end.
But I'll be able to see where you did it if you showed your work.
Okay.
So then, and I can be like, oh, you just, 8 out of 10 or something like
Okay.
that.
Okay.
Right.
Thank you.
All right. Remember, I'm trying to find ways to give you partial
No,
credit. So the more you explain your logic or show your work, then the more points I can give you.
I'm scared.
I'm scared.
Sorry.
Maybe show-
A healthy level of anxiety is okay for this. Don't panic.
Okay, but like.
Okay, we'll talk about that in a second.
Panic. The other, the other like exam thing that we
Yeah.
did. So if we do really good on that one, how does that affect our grade going forward when it comes to the final?
So this one is 100 points in your exam category.
Okay,
The take home is 20 points. So it's a total of 120 points in the exam category. Most of it's gonna come from this,
okay,
and then 20 of points come. It should bring your grade up, because I mean, almost everybody should be able to get, at least 15 points on the take home. And if you're worried about getting an A, then you should be able to get like at least 18 points probably on the take home.
okay.
Okay,
Thank you.
all right, I'll see ya.
Yeah. Yeah. Oh man,
It's okay,
no.
you're not taking it today.
I know, but like, we have to take it in the library, and the library's so loud, even though they closed the door. But I do get music, so
So
I
yeah,
can blast my music.
blast your music or white noise or whatever helps you stay in the zone. One thing I want you to keep in mind is the point of this is not to trip you up. That's why I'm giving you the exact test, basically, right? The point is to give you a chance to show me what you learned, and you've learned more than you think.
Yeah, but the story I failed last time.
Well, we can't do anything. We can't do anything about what happened last time, other than learn from it, right? So, do you learn any lessons from last time?
Yeah.
Like what?
Just like just everywhere last
Okay, we definitely haven't done that this
time. I
time.
missed like one match because I was sick, but I
Right.
did the data. So,
Right. So that's already gonna help you. That's literally 50% of the grade is labs at this point.
I mean, I already have a better grade than what I did like the last time, so.
Where's the computer? Let's look, let me look at your actual percentages, because you're probably sitting at like a 95 in assignments, right? In that category. So guess, if you're at a 94, then all you have to do is get 50%
Oh.
on the test, and you're gonna pass. Okay?
Well, now that I actually know how to go from grams to moles, I feel better.
That'll help.